Hello everybody, I am Vignesh Subramaniam from VALEO Thermal Systems, and today I am here to present our work on the topic identifying the optimal thermal conditions for lithium-ion cells under real-world aging and the need for adaptive BTM, which is also co-authored by Mr. Jeremy Blanda, Mr. Srinivasula Reddipelli and Mr. Mark Baronia. So here is the plan of the presentation. I will start with a brief introduction of lithium-ion batteries. Next, I'll be discussing step by step how to set up such an aging simulation platform. Next, I'll try to demonstrate how the battery aging phenomena behaves in a real-world scenario. Finally, I'll conclude my presentation with a summary. Lithium-ion batteries make use of lithium ion in order to store electricity. The anode is usually made up of carbon, cathode is made up of any metal oxide, and the electrolyte is generally made up of lithium salt solution. Lithium ion moves from anode terminal to the cathode terminal, producing electricity by converting chemical energy to electrical energy. Now the voltage provided to power the load is obviously very important. The figure here on the left shows the typical voltage discharge curve of a modern lithium-ion battery with a graphite anode as compared to the earlier versions which used to have the coke anode. Here you can see the flat discharge curve of the modern lithium-ion battery offers effective utilization of the stored energy in a desirable way. Finally, according to different packaging form, the lithium-ion cells are commercially available either in pouch, prismatic, cylinder or button configuration. Now let us discuss the typical battery wish list in context of an EV. For an EV, as we are talking about large batteries, 30, 40, 50 kilowatt hour batteries, the most important factor will always be the cost. What is the cost per kilowatt hour? Next, the energy, the specific energy density in watt per kg. This parameter will primarily decide the range of your EV. Next, the high specific power. The battery pack should be able to meet instantaneous power demand of the motor, which is mainly governed by the C rate of the battery. The question is, can I charge discharge at 2C, 3C, high rates, etc. Next is safety. Generally, high specific energy systems are often highly reactive and unstable. So we need to have a robust BMS strategy to ensure the safety of the EV. And finally, the lifespan. How long will the battery last, both in terms of storage time and in terms of operational cycle? At the moment, for example, most of the OEMs warrant around 70% capacity retention after 8 or 10 years. So this was the motivation for battery aging investigation, because as the battery accounts for around 40% cost of an EV, we wanted to understand what are the thermal conditions that can be maintained in order to extend the life of a battery. Now, lithium-ion cells age both with time and usage, reducing energy storage capability and increasing resistance to its excess. The aging pattern in a lithium-ion battery can be broadly divided into two types. First one is calendar aging, that is the battery degradation only due to storage, and it is highly influenced by the state of the charge of the battery and the temperature. Second one is a cycle aging, that is the battery degradation only due to operation, and it is highly influenced by charging strategy, again due to temperature and the operational cycle. And both of these in long term leads to capacity fade and power fade. And the motivation behind the current study was to identify what is the optimal temperature for lithium ion cells to minimize aging. Much of the industry today, they use electrical equivalent models for battery modeling, as the one showed on the left. There are some benefits to this modeling approach due to them being easy to build. However, some serious downsides are evident, especially if you want to simulate battery aging. The aging models here are empirically derived. The main drawback is that you cannot use these models outside the calibrated data range. On the other hand, if you see on the right, especially to model battery degradation, it is better to use physics-based electrochemical modeling approach like the one in Gamma Technologies GT Autoline. The main advantage is that you can measure important aging-related cell metrics like SEI layer growth formation. Another advantage is that by using these models, you can simulate outside the range of calibrated data. Now let us quickly have a look on the data required for building such a physics-based autoline electrochemical models. First of all, you need data to make the cell design. So you need the cell dimensions, chemistry, thickness of layers, size of active material, and the electrochemical properties, which can be user defined or you can take directly from GT Autoline material database. And then to calibrate the model, you will need the OCCV curve, open circuit voltage curve, discharge charge profiles, HPPC tests,